We do not pick a vitrectomy machine like we do a vacuum cleaner, considering its power, color, and brand name. Everything we ask the vitrectomy machine to do is so vital to the final result that we can't possibly be satisfied by a machine that only nearly achieves our goal. We ask for a precise control of the quantity of the vitreous that enters the endpiece in order to avoid aspirating or tearing the floating retina to which it is attached. Thus we ask for a precise aspirating flow control. We ask for a quick and efficient cut, without pulling out or moving the retina. And finally, we ask for a stable intraocular pressure during the entire procedure, and so we want the machine to adapt its infusion flow to the aspiration flow. The problems are that we are working in a complex environment with varying viscosities, and that the machine is not intelligent. It can only respond to our commands while also obeying the laws of physics. In this case, the laws of fluid dynamics. In order to understand this complex functioning, we are obliged to recall certain fundamentals of physics, and first of all, certain definitions. We can avoid talking about a vacuum, which is the absence of atmospheric pressure, minus 760 millimeters of mercury at Paris or New York. It seems more logical to deal with depression, a pressure inferior to the atmospheric pressure. To avoid any confusion, we will not use the term aspiration, but aspiration flow, which is a measurable physical property. The gradient of pressure is the difference between the upstream and downstream pressures. These pressures are always calculated using the atmospheric pressure as a point of reference. The compliant forces are those that change volume under the effect of depression. For the most part, they are linked to the elasticity of the walls and to the appearance of air bubbles. The laws of physics remind us that the flow of fluid in a tube is equal to the displacement speed of this fluid by the internal surface of the tube. The speed of the fluid is determined by the difference in pressures, the only possible motor for carrying out a fluid displacement. Fluid speed is slowed down by the forces of friction, which depend on the internal roughness of the tubing walls, and most of all on the viscosity of the fluid. The internal surface of the tubing depends on the tubing's diameter, and can also be influenced by the compliant forces under the effect of depression. To the best of my knowledge, only one experimental study has seen how the laws of fluid dynamics directly relate and apply to current vitrectomy procedures. The 2001 study by Jean-Christophe Bidet and Bernard Collin. They have allowed me to incorporate the results of their findings in this presentation. These authors studied the performance of different machines by measuring the actual flow and the actual depressions at the pump level. Pressure indicators at the test chamber level and at the exit of the handpiece permitted them to measure, with the help of very precise instruments, simultaneous pressure variations. To avoid all possible error in the comparative analysis of Venturi versus peristaltic, or classical cutting versus high speed, all other parameters were kept constant at each stage. The infusion liquid was BSS. The egg white was picked due to its heterogeneous and viscoplastic characteristics that are similar to the